algebraic action. Now I want to discuss again metric algorithms.
People will see on YouTube that I'm late every single time.
I'm sure people are counting your.
Yeah, I'm sure.
Okay, so of course, if you have a metrically ergodic action, then it is also ergodic. Of course, it is not the other way around. For example, the action of G on itself is ergodic, but it cannot be metrically ergodic. Because just take any space on which G acts isometrically, and take any point there which is not fixed, and send there via the orbit. This is a metric image. So is it clear that G does act on something isometrically? Take the regular representation. It's a Hilbert space. Take on which G acts unitarily, and take any point. So for a general Lebesgue space, metric ergodicity is strictly stronger than ergodicity. But now assume further that X is a classical guy. Assume X as, so a Lebesgue space is a space with a measure class. But now I want to assume that I have a representing in this measure class with an actual invariant measure as the probability invariant measure. So for short, we say that G acts on X, probability measure for the reaction. Then, for such guys, G is far from me to in general, then X is metrically as well. And the proof is trivial given what we've done before, because take X to U, assume you have, okay, no, U is the arithmetic action of G, etc. Then we have U on G. So assume I have a map with no fixed point. Okay. No fixed points. So assume I can send X. Well, if I send X to U, a map which is not essentially constant, it actually is sent to U minus all its fixed points. Right. So I can assume that U has no fixed point to begin with, and then the action of G is proper. And then I have a nice orbit space. This is the Hausdorff. And by ergodicity, X goes to one point here. Again, this is the same trick that we had before. And hence we hit the image, the plane image of this point. Well, the plane image of this point is some one orbit here in U. But orbits, the stabilizers are compact. So this is a copy. X goes actually to G mod K. K is compact. But now take the invariant measure here, mu, and push it by pi to pi star mu. You will get an invariant measure, an invariant probability measure on G mod K. I claim that you cannot have an invariant probability measure on G mod K when K is compact. Why? Let me explain. Take a big enough ball in G mod K will have more than half of the, assume I do have such a measure. This is invariant probability measure on G mod K. But there are no such. And the explanation I'll give you. If a big enough ball in G mod K will contain at least one half of the mass. And then you apply any element G in G to that ball. It must intersect itself because the measure is preserved, and the image of that ball will have more than 1/2 of the mass as well. So it must intersect the previous one. So this ball cannot be moved to infinity. But because K is compact, I can obviously take a G that does takes everything to infinity. Maybe let me summarize this, because maybe when I write it down, I will use another terminology. I don't know if you know, because the action, a PNP action is recurrent. This is called recurrent. Recurrence. So if I apply, okay. Now, is this coming now? Recurrence. The concurrent and the action of the K is not. But basically what I said already is an explicit explanation why this could not happen, and this is a contradiction. A contradiction to what? To the existence of such a non-constant pi. Okay. And now I want to discuss what it means to be metrically harmonic for probability measure preserving space X. So forget Lie groups at all. So this is now this is a theorem, or maybe definition first. Here's a classical definition in ergodic theory. G act on X. Or maybe I start with the theorem, and then I'll assume G generic act on X is a probability measure preserving action. Then the following are equivalent, following three properties. One, X is ME. Two, for every ergodic action of G on Y, G on the product action is also ergodic. So this is stably ergodic. Usually when you take an ergodic action and take the product with, this is PNP as well, probability measure preserving, and take the product with the probability measure preserving, it is not ergodic anymore. Think in your mind of the action of an irrational rotation of the state. It will not have this property. In fact, if you take the double, if you take that space times itself, it will not be ergodic. And it's not a surprise because those things should be equivalent. G on X times X is ergodic. So this is methodology speaking. This is stably ergodic. And this is double ergodic. So there are some implications between those things that are true in general, but for probability measure preserving actions, they are all equivalent. And definition, G act on X is called weak mixing if the above is satisfied. The properties are satisfied. So again, this has nothing to do with anything that we've seen so far. So it's completely independent. Let's prove it. The implication 1 implies 2 is something that we more or less have seen. We have seen a similar argument. So assuming x is ME, and now consider f in L2 x times y, which is invariant. I want to prove that x times y is ergodic. So I want to show that f is constant. The thing is that I can use f. F is a function from x times y to c, which is G variant. But I can view it as a function in the first variable to functions in the second variable to c. So view it as, maybe I'll take L3 just to be sure. I want to use L2, but I want to use a function from x to function from y to c. And the G variant, so here G acts on y, so it acts on this space as well. And this is by the G invariant of the function, this function here must be equivalent. Now, this is not a nice metric space, I mean, with the L-infinity metric, because the action of G is not continuous in this space. So, but this is probability measure preserving y, so I can view it as a subspace of L2y on which the action is continuous. And this is my function pi from x to some u. The action of G here is as my f, or maybe call it f must be constant.
Can you say again? I was sleeping for a second.
Yes.
Why do you go to it?
Okay, so first of all, what I'm doing, there are two things I'm doing. One is a completely formal, taking a G invariant function here and view it as a G equivalent function from that G space to that G space. There is no problem here. Now I want to view that, I want to use the ME property, metric modicity property of X as a G space. So I want to view that as a metric space. But I guess I was not paying too much attention when I wrote the definitions previously, but when in the definition of metric modicity, the action of G on U, the metric space, must be continuous. I don't know if I did write it down explicitly, or it was, I hope it was understood. It was not just an isometric action on a metric space without respecting the topology of G itself. G is not an arbitrary sum of the isometric group, or there is no arbitrary map from G to the isometric group U. This map must be continuous. And this is not the case here. For the L-infinity law, take L-infinity G, just to understand this. Take the characteristic function of some measurable set. And take an element which is not identity in G, but arbitrarily closed. And shift this characteristic function by this element from the left. You will get another function. Yeah. So the distance between your two functions will be actually 2. So the metric here, I mean, G does act as a metric here, but not continuously. I mean, every element of G is a continuous function, of course, of that metric space. But the map from G to the isometric group is not continuous. The action map, G times X, G times U, is U, to U is not continuous. But if I take the L2 matrix is the case. And those things are standard. So I don't want to explain this. And because Y is a probability space, an infinity function is L. So I can apply now to this metric ergodicity and conclude that the image of X is constant. F must be a constant function. Must be yeah, it must be a fixed point. Maybe a fixed point to begin with. F, the image of F. If it wouldn't be a functional space, I would say that F as a map must be a constant function. The image of it is a fixed point. This fixed point will be in a minute a constant function here. I just don't want to write it down yet. It must be a fixed point in L2YG. I mean, the image of X must be big F must be essentially constant. It must be essentially constant, and the image of it, of course, must be G invariant. Y is ergodic implies that L2YG is a constant. Constant function from Y to C. And this constant, actually, if you think of it, is the image of every pair of points, little x, little y. Little x goes to that function which takes every little y to that essential image, and f is constant. Which means again that this is ergodic. Okay, so this proves 1 implies 2. 2 implies 3, I guess, is more the reality. And 3 implies 1. So I'm assuming that X is doubly ergodic. So maybe first of all lemma. X doubly ergodic so actually I should say that the indication 3 implies 1 has nothing to do with probability measure possibility. This is a general thing. So actually I will prove it in that generality. It's slightly even easier for probability measure observing, but not that much, so let me. So if X is doubly ergodic, that means X times X is ergodic, then there is no countable image of X. No X to a countable G set. G conventional.
Why can't you just take the distance function, move this function x to a metric space, and you take distance of fx and fx prime is a function x plus x?
Yeah, this is what I'm doing. Maybe okay. Maybe I'll explain. Yeah. You have the map from X to U. And here's what I'm about to do, but I will need preparation. I will again. Here's an assumption that I don't remember if I wrote down or not. I am assuming that U is separable. The metric space. Actually, this is not needed. It could be shown that whenever you have a map from a algebraic space into a metric space, the support of the image is separable. I don't want to show it, but let's assume that. But now, look at the image of X in U, and take actually a pair of points in X, and look at each image in U times U, this pair of points in U, and I can measure the distance. The distance of the images will be a function on X times X. And because the metric is invariant, and the map from X to U should be equivariant, this function should be constant. Ergodicity of X times X. And this constant, well, if this constant is 0, I'm done. All the points are, almost all points are in distance 0 from each other, so this is just one point. If this distance is not 0, maybe it is 1 or whatever, epsilon, if it's bigger than epsilon, I can find an image of X in my space. But my space is separable, so if X is not separable, this image is discrete. Every 2 points are in big distance, the distance epsilon from each other. I have a big discrete subspace in my space U. Okay, that's fine, unless maybe I have a countable factor of X. Maybe it could happen. But I claim that you cannot. So then actually, it's kind of a disclaimer. I can't have a countable factor of X. Because, I mean, every function from X to a countable set must be essentially constant. Every such must be constant. So just a minute, finish. So note. So push the measure from X to C. So this is an atomic measure on C. And now I claim that C times C I can view as the diagonal union C times C minus diagonal. Of course. And both have, if the image is not essentially constant, both have a non-trivial measure contradicting ergodicity. Or take the function which is 0 here and 1 there and put it back to X times X and get a non-trivial, contradict ergodicity. Yes, Miet?
Yes, so the reason that you need this argument is, and you can't just say that this distance function and then
Oh, now I'm about to write down the argument that I just said previously.
Yeah, but the reason that you need that, and you can't just say that this distance function that diagonal is 0 is because it might have 0 measure, and they are essentially constant.
Well, yes. If you have a space with a measure, when is it that the diagonal in X times X and measure times measure, when is it that the diagonal is non-zero, is not an R set? This is if and only if you have an atom in your space. For a countable space, you always have atoms. Now the proof 3 implies 1, precisely, and this is what I already said, writing out properly, 3 implies 1. Consider periodicity of x times x. This composition is constant. If C is 0, well, the image of pi is constant in U. If C is not 0, the image is a discrete uncountable dilemma. Set contradicting superability of U. Or if you want, contradicting. I claim, and I will not do this, like basic measure theory, that the Lebesgue space I cannot decompose into uncountable sets. Each of them as if I do decompose it into uncountable sets, maybe let me say it for this uncountable set will be a discrete set of U, and every union of it will be measurable. The drainage of every union of points here will be measurable. So this will be a partition of X for which every union is measurable. And the measure mu on X, take a probability measure on X. This is not invariant, this probability measure mu on X. It's not G invariant, or it's only measure class invariant. But yet, I claim that there is a probability measure on X and an uncountable union of X such that you can measure each subset. I want to claim that for all but countably many pieces, the measure will be 0. Again, this is a standard argument I probably are familiar with. Ask yourself how many pieces I can find with measure bigger than epsilon for some epsilon, bigger than 1 over n. By the fact that these pieces are disjoint, you have only finitely many. And the fact that mu is a probability measure, you have only finitely, and this for every n. So take the union over n, and you find that all but countable many are actually measure 0. So what you find actually that this image must be counted on contradicting the lemma. Okay.
So that's the proof that the image of a Lebesgue space, the metric space is
No, this is proof that the image cannot be discrete. So the image, in my mind I want to rely on this more general fact, or only now I realize that I don't need to, but it is a fact that indeed the image must be separable, but this I don't want to go into it. This is really about X being a Lebesgue space, and definition of a Lebesgue space. Okay, again, so these 3 facts are the same for probability measure preserving actions, called weakly mixing with the classical notion, and this notion is equivalent to the metric periodicity notion that we studied. And back to simply group G, we see that every probability measure preserving action, well, ergodic one, is metrically ergodic. So if x is metrically ergodic, if x is weakly mixing, then x times x is ergodic. Take this to be your y. You get that x cubed is ergodic, etc. X to the n is ergodic. Corollary of whatever. X with mixing implies x to the n ergodic for all n. Then we get g act on x to the n is ergodic for every n. And actually we have seen in the last class that if g act on something, on a probability measure preserving something ergodically, or metrically ergodic, then okay, maybe, then g act on x to the n is ergodic as metrically ergodic. Right? And also, this we've seen last time. If we have u in G, you need to put a book. Or actually any. Oh. It's slightly more general than that. Then u act on x to the n is ergodic for everything. Age changes to non-compact. Here's a more general statement. Okay, so up to now, this is just a simple corollary I thought we did today, and these two lines requires us to go back to what we did last week. So just to remind you. Y, that's the line. So first, G mod H, I claim, is ME. We have just seen last hour that whenever every action of G, there is no metric here. Whenever G acts, there is an invariant metric on some space. The action is proper, and stabilizers are closed. If there exists invariant metric on G mod H, then stars are closed. The action is proper and stabilizers are compact. This is the theorem that we proved last hour. 2. Last week we've seen G act on X probability measure preserving. This is very similar to one implies 2 that we just had before. Probability measure preserving, ergodic, G act on G mod H, metrically ergodic, implies F H act on X, ergodic. So this is a statement that we proved last time. this has nothing to do with Lie groups. It's a general implication that we had. But of course, now if G is one of ours, then for every non-compact H, G apt on G mod H metaterabolic, and the ergodic action of X on whatever is still agentic. I mean, this need not be metaterabolic anymore. Yes, please. Never mind. So, what have we done so far? We started not so long ago to discuss, we're studying algebraic groups, we study algebraic representation of arbitrary groups, we start discussing algebraic representation of ergodic actions. What we've seen now is examples of many, many ergodic actions of groups. I mean, we developed general theory, but now examples of ergodic actions I can give, which are quite explicit. For example, take, I don't know, take gamma in SL3R lattice. For example, SL3. Then take this to be G mod gamma is G ergodic. Of course it is. It is transitive. But also it probability measure preserving. Then take Q, I know, to be this guy here. So it acts on, I don't know, this G mod gamma is transitive G action, but G mod gamma to the n is not transitive anymore. The fact that G acts ergodically here is not a trivial fact. The fact that U acts ergodically here is not a trivial fact as well. And we have many of them. This is just an example. If I'll do it in SL2, the fact that, just to give name, the fact that this guy acts on SL2R or SL2Z, and also this guy. Those are very famous examples. Not trivial. I mean, we understand it very well now, but those are famous from geometry. This is called whole cyclic and geodesic flow on the modular surface. They are ergodic. Basically we prove this. And we proved a lot of generalizations of those. So our proof was by structural theory of semi-simple groups. Now, how am I in time?
3:20. 10 minutes to
10 minutes
to coffee.
Okay. So let me try to do something. Yeah, it is coffee not today, not tea. Why? Not this. Okay, now let me prove here. Let's S act on X. Rebecca, okay? Assume for every n, S act on X to the n is ergodic. E.g. X probability measure preserving this is exactly what we call weak mixing in the probabilistic micromodular case. Okay, this is our encoding data. Let G be algebraic. Over a local field. Oh, actually, valid. One of those guys that we studied. Let assume F M is a risky dense algebraic representation. So algebraic representation here just means a continuous homomorphism into this algebraic. Well, when I write G, I mean the points over the field. Then you remember that under this situation, we had the category of representations of X, and it has an initial object. So this is the general setting that we had, plus this weak mixing assumption that I'm adding. Under the Bodisky assumption, we had an initial object. We proved that one. Now I'm asking myself, what is happening if I add this extra egoistic? And the claim is that then the initial object of the category of representation of X is a point. That is every map. This exactly means every equivariant map X to V is S up here, G up here. This is supposed to be algebraic, is essentially constant. That is, there is the map from X to a point, and that point is mapped here in a commutative way. So the image of it must be the image of X. So, shall we commit now, and or should we take a break and?
Coffee is only in 5 minutes.
Hmm?
Coffee is only in 5 minutes.
Yes, but if I start proving it now, I will not finish.
How long is it?
Probably 10. I don't know. Okay.
Go for it.
Hmm?
Do it right now.
Let's do it. So I'll just remind what we've done so far. So far, we've seen that every G-ergodic space is absolute weak mixing. It has all the X to the N being ergodic, and this also is a restricted reaction to a subgroup, an uncommon subgroup of G. And now I'm studying algebraic representation of such things, and I'm saying that they are all trivial in some sense. I can map a weak mixing thing into the algebraic variety. I can always do such things if I fix points, but this is the only way to do it.